Hi, everyone. Today is part one of our center of mass to wrap up this chapter. Today, we're going to start talking about studying the motion and momentum of some complicated system. Right. So far, we've used spheres, blocks, bullets, hockey pucks, pretty simple objects. But what if we have an object that's not so simple? So we don't want to have to calculate for each particle in an object. We're going to need a shortcut. So for an example of moving objects and taking advantage of the center of mass, we can talk about high jump. So high jump is an event in track and field. This person is jumping over a really high bar. This is, I don't think this is an actual picture of him, but Dick Fosbury is the one who started this trend, this technique of doing the high jump in this way. It's called the Fosbury flop. And what you would do is you run up and then you jump head first backwards to try and get your entire body over the bar. However, at any given moment, right, you do not have that much of your body over the bar, right? Other techniques require like running at the bar and like swinging your leg over. They all basically involved getting almost your entire torso up above the bar. But this technique actually allowed you to have a pretty small amount of mass over the bar at any given time, instead of having to get a lot of mass way much higher than everyone else. So Fosbury set the record in 1968 using this method with the 7-foot 4 1/4 inch Olympic record using this method. But that's just an example of how utilizing center of mass can actually be advantageous. So what we're going to do is we're going to talk about two different ways to do center of mass. Okay, so first, a particle method. Okay, if you want to use a particle method, you want the center of mass. You would take the mass of the particle times the position of the particle. This is just some distance from whatever you define as 0. Right? X is just a distance. Then you have the mass of a second particle times the distance that particle has from your 0 point. Then divided by the summation of masses. Okay, say you've got two particles. We'll actually do an example down below. But this is how you can find the center of mass of a couple particles. You can even do this for 2 or 3 particles. We'll do that later in this video. Now, if you have a more complex object, say there's tons of particles, like a body, right? So then it gets a little bit more complicated. We'll set this up as a sum from n equals 0 to n equals I of mi xi divided by the summation of n equals 0 to n equals I of mi, right? This is a summation. We don't use summations a whole lot in this class, but this is one way to notate how you can take, m1 x1, m2 x2, m3 x3, m4 x4, all the way up to an extremely large number in a summation or in a series like this. We will actually discuss this method later on in this video. But first, let's talk about this particle method. Okay, this is not the most efficient way to do it, but if you've only got a couple particles, then you can make it work. So our example first is the separation between a hydrogen atom and a chlorine atom in a hydrochloric acid, or HCl. Okay? So we have hydrogen, really small. It's at a mass of 1 AMU. That stands for, what is it? Atomic mass unit. Right? Then you've got Cl that is really big compared to hydrogen. It's 35 times bigger. It's 35 AMUs. Right? Now, the distance between them is 130 picometers, and we want to determine the location of the center of mass. So we have the mass of hydrogen. I'm going to zoom in so a little bit easier to write. Mass of hydrogen is 1 AMU, and then the mass of chlorine is 35 AMUs. Now you can do this two different ways. Remember that the x up here in our equation, it's the distance from your 0 point, right? Well, if you got to determine what you want your 0 point to be. So first, we're going to do this where the 0 point is hydrogen. Then I'm going to do the problem again where the 0 point is chlorine, just to show all of the possibilities, right? So we've got position of hydrogen is 0, and then the position of chlorine, is 130 picometers. Picometers is a really small unit of distance. I think it's 10 to the negative 12. 1 second. When you look at the AP equation sheets, it is, 10 to the negative 12 meters. It goes milli, micro, nano, and pico, going down by threes. So picometer is a distance that we see often when we're talking about atomic distances. So let's do this one first. Okay? This is relative to hydrogen. So I'll actually say XCM hydrogen. Okay? So we have the mass of hydrogen times the distance of hydrogen from hydrogen, plus the mass of chlorine times the distance of chlorine from hydrogen, divided by mass of hydrogen plus mass of chlorine. Okay. The distance from hydrogen to hydrogen is going to be 0. So here we have 35 times 130 divided by 1 plus 35. If you put that into our calculators, we're going to get 126.4. Picometers, and that is the distance from the hydrogen atom, right? 126 picometers from the hydrogen atom. So that's most of the distance, right? I mean, that puts us about right there, right? I'm going to just estimate that, right? So we've got 126.4 picometers from hydrogen. It's really close to chlorine, right? Now that's how you can find the center of mass, but we can actually change our relativity, right? Let's say that now we want to find it relative to chlorine. So now hydrogen is 130 picometers from chlorine, and chlorine is our 0 point. Right? So now let's whatever. So let's find the center mass with respect to chlorine. You've got mass of hydrogen times the position of hydrogen plus the mass of chlorine times the distance of chlorine from chlorine, which is 0, divided by the mass of hydrogen plus the mass of chlorine. Okay. So here you have 1 times 130, right? 1 times 130 divided by 1 plus 35, and that will give you 3.6 picometers. So if we come up here, notice that there is only 3.6 picometers left. So if you add those up, it actually gives us the full 130 distance between the two. So if we look and find the distance relative to chlorine, it's really close to chlorine, which makes sense because chlorine has most of the mass of this two-particle system. If you do it relative to hydrogen, you'll notice it's really far away because hydrogen has a lot less of the mass in this system. Okay? So that's how we can use the particle method to find the center of mass. But what if we have more than 2 center of masses? Or what if it's in 2 dimensions? Now we have x's and y's. So we've got a system of 3 particles as shown. Assume M1 and M2 are both 1 kilogram and M3 is 2 kilograms. So let's get our givens. We've got M1 is 1 kilogram. M2 is also 1 kilogram. M3 is 2 kilograms. Now, what we want to note before we calculate the center of mass is their location, right? So the location of M1 on this XY grid would be 1, 0, right? That is its location right here, right? Then the location of M2 would be 2, 0. And the location of M3 would be 0, 2. Okay, we're just looking in XY plane coordinates. Now, if we want to calculate the center of mass, the center of mass is going to be somewhere in this grid. So it needs to be in terms of X and Y. So what we'll do is we will actually find the center of mass along the X-axis, then we'll find the center of mass along the Y-axis. So we will do that down here, zoom a little bit. X center of mass would be mass of 1 times the X value of 1. Plus mass of 2 times the X value of 2, plus mass of 3 times the X value of 3, all divided by sum of masses, right? So we can say first off, mass 3 has no X dimension to it, right? It has no X position. So we can say that that goes out to 0. So you've got the mass of 1 times the X value, which is 1, plus the mass of 2, times the X value of 2, divided by 1 plus 1 plus 2. Now notice here, we still keep mass 3 in the math, even though we are disregarding it. We canceled it out because there's a 0 there, right? Common to get rid of the X position. That's really common to do. Because there's a 0 there. We do that often in our math, but that doesn't mean that you can cancel it on the bottom. A lot of students make that mistake. So be careful when you're doing that to not cancel it in too many places. This will give you 3 divided by 4, which you can say is 0.75 meters, and that's for the X. Okay. Now we will do the center of mass on the Y. We've got M1, the Y value of 1, plus M2 times the Y value of 2, plus M3 and the Y value of 3, divided by the sum of masses. Now, if you look up here, 1 and 2 are both only in the X axis. So now we can say that the mass of 3 is 2, the Y value of 3 is also 2, divided by 1 plus 1 plus 2, gives you 4 over 4, which is 1 meter. So that means that our center of mass would be 0.751, which actually turns out to be this red X that was there the entire time. So that's how you can find a two-dimensional center of mass by finding the center of mass in the X, center of mass in the Y. Now, what if it's more than just XY plane, right? What if it's an actual object? So when and how should we use calculus to find this? So what we want to do is we want to derive a general expression for the center of mass of an extended rigid object using calculus ideas. Now, if you want to integrate across mass and distance, or if you want to calculate the center of mass across a distance, that's what integration is really good at. It's trying to do math across a distance or across a time, right? Across something. Integration is best for that. So what we'll do is we'll actually start with what the AP exam gives you, which is the summation, so the center of mass is the summation of mi xi divided by the summation of mi, right? Mass times position divided by mass. Now we will integrate this. Okay? We will integrate that position with respect to mass divided by the integral with respect to mass. Okay? Now, we could integrate dm, right? If you integrate dm, you just get m, right? So you really just have the integral of x dm divided by m. So that's not too difficult. But integrating x with respect to m, it's kind of hard to integrate across mass, right? You're like, what would be your beginning and end value in this scenario? When you're calculating center of mass, integrating across mass is kind of a tricky concept. But what we can do is we can talk about density. Okay, so there are 3 types of density that we'll talk about in this class. The first one that everyone is familiar with is volumetric density, and that has the symbol rho. which is like a curly P, and that is mass divided by volume, right? Or you could say that is dm divided by dv. Then, but what if you don't have volume, right? Volume is specific to 3 dimensions, right? It is 3D space that an object occupies. But what if you don't want to analyze all 3 dimensions? Maybe you just have area. So there is actually something called area density. That uses a lowercase sigma, like that, and that is mass divided by area, or dm divided by dA. Now, what if your object is even more simple than that? What if it's just got 1 dimension? Well, then that is called linear density, and that is shown by lambda, and lambda equals mass divided by distance, or length, so that would be dm divided by dx. Okay? Now, in our integral, you'll notice that we have similar variables. We have x and m, right? So here, if we want to substitute out that dm because it's being kind of complicated, let's solve for dm, isolate it, and then substitute. So if we multiply by dx, you have lambda dx equals dm. And now we can actually substitute that up here. So let's say we have the integral of x times lambda dx divided by mass. Okay? Now that is something that you can actually use. Now, that integral doesn't mean a whole lot if we're not going to use it. So that's a nice equation, but let's jump ahead and let's use that in a practice problem. Okay, let's prove that the calculus method for center of mass actually works. So we want to find the center of mass of a uniform ruler of mass m and length L, as shown here. Okay, you've got length L. There is nothing in the y-axis. It is only measured in the x. You've got dx. You've got dm that equals lambda dx, just like we said. Okay. So first, what does common sense tell you that the answer is going to be? Well, if we have a massive uniform density, okay, it is a uniform ruler. So if it's uniform, that means that the density should be the same all throughout, which means that the common sense answer would be L divided by 2, right? You just take the length divided by 2. You've got the middle, right? It should be right in the middle. Now we're going to use calculus to prove that that common sense is real, or is correct. Okay? So we want the center of mass. We have the equation, the integral of x dm divided by the integral of dm. Okay? But we also know that it has uniform density, and it would be linear density, shown by this dm equals lambda dx, okay, linear density. That would be dm divided by dx. Therefore, dm is equal to lambda dx. So let's actually plug that in up here. We have the integral of x times lambda dx divided by, we can actually put lambda dx here too, integral of lambda dx. Now, it's also best, if you can, to give your integral bounds. So we'll go from 0 to the length L to make sure that we are getting this in terms of the length. Now, if you have these two integrals divided, it is going to be easiest to do the integral separate, then put in the answers and simplify the answers instead of trying to jump the gun and do it at the integral stage. So let's do the bottom one first. It is going to be the more simple one. You've got the integral from 0 to L of lambda dx. Okay. So if you have the integral of a constant with respect to a variable, and the variable is not present, the integral is not present, you will just multiply in that variable. So you would get lambda times x from 0 to L, right? And that means you have lambda times L minus 0, which gives you lambda times L. Right? So we'll bring that on up here. That is lambda L in the denominator, right? Now, if we want to do the numerator, we have the integral from 0 to L of x times lambda dx. Now there's actually an x to integrate, so we will bring the constant out front. That is times x squared over 2, just integral of x, from 0 to L, which means that you then get lambda times L squared over 2 minus 0. Okay, so then you really just get lambda L squared over 2, right? So let's bring that on up. We've got lambda times L squared divided by 2. Now we can also notice that immediately density cancels. You can also cancel one of those L's. Once all the cancellation simplification is done, lo and behold, you get L over 2. So that is how we can use calculus to find the center of mass. In part 2, we're going to expand a little bit on how we can use calculus to find center of mass. For example, what if lambda is a function of x instead of just lambda? We'll continue that on in center of mass part 2, and that will wrap up chapter 9.